Yep, looks good.
Okay, so I'll spend about 20-30 minutes to provide some highlights on the ORV3 BBU shelf specification, technical specification, features and requirements. Okay. By the way, the spec is already available in the OCP community. So yeah, these are the technical specification highlights. It's gonna be a 2 OU height power BBU shelf fit in the ORV3 rack. The output voltage is 47 volt to 48 volt from 100% load to zero load. So the middle point is 47.5 volt. The output power is maximum 15 kilowatts with 5+1 redundancy and 5 minutes backup time. The BBU shelf consists of a PMC module or PMI module and the 6 3-kilowatt BBU modules. The BBU module, inside each BBU module, there's a battery pack, there's DC-DC charger, there's a DC-DC discharger, and there are also battery control and communication circuits. The BBU charge from and discharge to the rack bus bar. The BBU shelf is flexible location within the rack. You can put it on the top, you can put it in the middle, you can put it at the bottom of the rack. It has direct communication through the PMC to TOR. The operate busbar connector and the PMC module is the same as power shelf. The BBU modules are interoperable with different suppliers. Okay, let's quickly compare the V3 BBU solution and the V2 BBU solution. The current V2 BBU solution, the battery pack, is a slave of the power supply. So it charge and discharge through the power supply. And so the battery pack has 90 seconds capacity. The V3 architecture, the BBU shelf becomes independent from the power shelf in terms of charging and discharging. So there's no communication or directly link between the power shelf and the DC shelf and the BBU shelf, except the bus bar. So the BBU capacity now is 5 minutes for higher reliability in the data center. So compare the V3 BBU and the V2 BBU, the size. ORV2 BBU, we have two 1.5 OU BBUs. So the total height is 3 OU, but the ORV3 is only 2 OU. And the ORV2 provides only 90 seconds, and the ORV3 is 5 minutes, 300 seconds. ORV2, the BBU output voltage is a battery voltage, is a wide range. And ORV3 is regulated 47.5 volt. And the charger discharger ORV2 is inside BBU, inside PSU, and ORV3 is inside BBU. The communication, there's no direct communication from BBU to the TOR. But for ORV3, the BBU modules communicate through Modbus to the PMC, and PMC communicate to the TOR. So this is a high-level BBU internal block diagram. It will have a battery pack with the BMS and the MCU for all the control and the monitoring and the controlling communication. It has aux power for the fan and the MCU power. Okay, it has a 3 kilowatt discharger, DC-DC converter, 3 kilowatts. It has a charger DC-DC, which is 250 watts. It has the O-ring for the output, hot swap for the input, and the fuse for protection. Okay, the battery pack we plan to use for 5 minutes capacity, we plan to use 12S6P lithium ion cells. This we found is the most suitable for our application. The discharge power, including the discharger efficiency for the battery pack, will be 3.15 kW for 5 minutes. We can guarantee this number at the end of 4 years and with 35 degrees C ambient of data center. But we expect the BBU life to be 8 years, so we can reuse the battery backup shelf for another 4 years. There's BMS of BBU controller for all the cell voltage balancing, control, SOH test, smart charge control, and protections. It also provides monitoring and communications. There will be a resistor fuse required by safety for permanent battery failure. It will be safety compliant. Okay, we're gonna apply safety compliance at cell level, pack level, and the module level, and even shelf level. Okay. The discharger input is from the battery, so it has a wide input range up to 48 volt. The output is 47.5 volt with a range from 47 to 48 volt. The continuous maximum load is 62 amps. Minimum load is 0 amps. And it has a peak load capability same as power supply shelf. So it can support IT gear transient load. The output startup time must be within 2 milliseconds to avoid a voltage dip over spec on the bus bar. The low transient response has to be within plus minus 3% of the regulation band. The efficiency of the discharger has to be greater than 97%, including all the input fuels, O-ring, and hot swap to meet the thermal requirements. So the output voltage is adjustable for SOH test. So we're gonna raise the module voltage to let the module share current from power shelf in the SOH test. In the overload condition, it has a constant current characteristic, same as power supply. It has also active sharing in a normal operation. Okay. So I did highlight this is also included in the spec. I want to highlight there here is the BBU and the PSU voltage setting has to ensure there's a margin for BBU to activate and exit. So the target, right now, the worst case, we have 0.875 to 1.35 volt margin. The setting point between the BBU and the PSU is the maximum BBU output voltage is 48 volt. The minimum PSU output voltage is 50 volt. So there is minimum 2 volts gap between the BBU output and the PSU output setting. But we have to consider the corner case conditions like load transient and the set voltage tolerance. So after all this analysis, we can see with the BBU activate. Margin 1, for example, margin 1 is when the bus voltage drop to 47.5 volt or lower for more than 1 milliseconds, the BBU will activate, will kick in. And based on the analysis, the PSU minimum transient voltage is 48.875 volt. So we have 1.375 volt for the BBU to activate. There's 1.3575 volt margin. So when the bus bar voltage is the BBU exit threshold, the green line is 49 volt for greater than 200 milliseconds. So when the bus bar voltage returns to greater than 49 volt for longer than 200 milliseconds, the BBU will exit, will stop discharging. So the gap analysis shows we have 0.875 volt margin to avoid forced exit of the BBU because the minimum PSU static voltage is 49.875 volt. That's the purple line on the top. So there's a third margin. Margin 3 is so we want the BBU not force trigger the BBU exit. Yeah. The light blue line is the BBU maximum static voltage is 48.1 volt. So compared to the PSU, compared to the BBU exit threshold 49 volt, we have 0.9 volt margin. So the BBU maximum voltage will not accidentally exit from discharge. Okay. So another key point we're gonna implement, I think Hamid will implement in the power supply to avoid the voltage transition from power shaft to BBU shaft. So on the top, there are two charts, two joints. The top one shows the original design. So when after AC outage, there's a hold up time period. So because in the V3 architecture, there's no AC link to the BBU. So BBU doesn't know the AC is gone. So BBU has to constantly monitor the busbar voltage to activate. The problem is at AC outage, the PSU voltage has a hold up time period of about 20 milliseconds, then start to decline quickly. Since the BBU needs a few milliseconds to activate and ramp up, so the voltage dips below the regulation band and may cause the IT gear reset. So the idea is, the solution is, at AC outage, the PSU proactively adjusts its output voltage lower to below 47.5 volt to activate the BBU during the hold up period. You can see the PSU output voltage drops within the 20 milliseconds in order to notify the BBU it's the time to activate. With this solution, we're gonna have no glitch during the transition. This is very important, okay. The charger, now talk about the charger. The charger has input from the busbar, which is from the power shaft. It's well regulated, around 50 volt. The output has two operation modes for the charger. One is the constant current mode. before the voltage reaches fully charged, it's in a constant current mode. The constant current is configurable through the communication. It has a range from 0 amps to 5 amps. The pros and cons for higher and lower charge current is, with higher charge current, you recharge the big batteries faster. But the concern is it will take more power from the power shelf. So each one is 250 watts, 6 of them is gonna be 1.5 kilowatts. That's 10% of the power budget. So in that case, we can lower the charge current, even defer the recharge to 0 amps. So we can do an off-peak recharge. Then when the battery voltage reaches close to 4 volt per cell, it enters CV mode. The charge current will be below 0.5 amps. And the regulation has to be tightly regulated because the battery, if the battery voltage is too high, it will compromise its life. So we want a plus minus 0.1 volt regulation at CV mode. Communication is the same as power shelf. I believe it's already covered. It's gonna be universal shelf monitoring and the control module used for both battery and power shelves. The communication for short term, we're gonna use Modbus RTU mode, which is PMI. The long term, we might have the PMC as a Ethernet communication. And it also provides a couple GPIO, some GPIO signals for controlling and monitoring. It has a single bus for communication with BBU and PSU modules, which will be the Modbus. It supports remote firmware upgrade. You can also control by writing to the components. Yeah, we also need to evaluate the cooling of the PMC module because it doesn't have a fan. Okay. Some mechanical parameters, the dimension, the weight, it will be heavy, like a 15 kg shelf only, and the 55 kg fully populated shelf. It will be compatible with ORV3 rack and the standard rack. The BBU module dimension and the weight, each BBU module is 6.5 kg. It has a foldable handle to minimize the front end protruding. It has a keying feature to avoid wrong installation. Yeah, it has a connector protector to prevent the connector damage. Thermal. So thermal has to support 3 operation mode. In the standby mode, we also have the fan running to push out the hot air from backflowing into the BBU. So we're gonna keep the fan with minimum, with low speed to keep the cell temperature low to prevent the degradation of the cell. In the charging mode, we should enable the recharge within 30 minutes of discharge. In the discharge mode, we have to support 5 minutes discharge with full power, keep the temperature rise within target. So this is a picture of the final product. So you can see there are 6 BBU modules and 1 PMC PMI module. And the draft of specs and prototype systems are on the BBU website, on the OCP website. Your feedback is welcome. Currently, This project is in the POC stage, proof of concept stage. There are also related presentations today on the ORV3. You are welcome to join. Okay. So I have the next few minutes for questions and answers.
Thank you, David.
Okay.
Finally, we have somebody finishing the presentation on time, leave some time for questions.
Okay.
This is great. Let me go over the questions.
Yeah.
Piotr, if I pronounce correctly, is asking, is there an option to locate BBU in a separate room nearby to IT rack itself? The reason for this is to use bigger battery to achieve longer backup time.
Sorry, I didn't get the question.
So the question is that basically, can we have this BBU system not inside the rack, but somewhere else, like keep it in a battery room and keep stacking several
No.
of them together?
Yeah, it's not possible. It has to work with power shelf in the ORV3 rack. So it's still combined with PowerShell because the charge and discharge comes from PowerShell.
I see. Okay, so
Yeah.
that's a different design.
Right.
They want to have a battery room.
No. Yeah, it's a if you want a battery room, that's a different design.
Okay. The other question is that why do we need up to 5 amp charging power?
That's the original V2 design. The charge time will be much faster at 5 amps. For example, that will reduce your waiting time for the battery, for the rack to be ready. Before the battery is fully charged, the rack is not safe for use. The users has to wait until the battery is fully charged, then they can load the software applications.
Okay. What is the default time then?
Default charge?
The default charge time.
The default charge current or charge time?
Default charge current.
Default charge current, I'm going to set it at 5 amps for now, but it will have a variable charge feature. So depend on, excuse me, depend on the discharged energy, we can calculate what will be the recharge current.
I see.
So there are different charge modes. The initial power up, a short AC outage, a long AC outage, and the charge current should be different. And there's also theoretical charge mode, SOH. After SOH test, we also need to charge the battery back. So in all these different modes, we will define the charge current case by case.
I see.
Yeah.
So basically, there is a variable charges. So the users can set the different values between 1 to 5.
Yes, 0 to 5.
0 to 5.
Yeah, some of the users, they don't want any charge current at all because even 1 amps charge current consumes 300 watts per rack, right? We have 6 of them. So 300 watts still could have some impact to the power capping. So in that case, the user, they can command the BBU shop they can write 0 amps to the charge override register. So that means the charge is stopped, is deferred until off-peak hour. They can select the off-peak hour to charge the battery.
See, thank you.
Mm-hmm.
The other question is that are there different power options for the BBU modules with different capacitances or runtimes per BBU module?
Sorry, I don't get the
So, but the
question.
basic question is that, would there be
Mm,
different power options? So this one, I guess the module is 15 kilowatt.
mm,
Would there be a higher power option, or would there be another battery with different backup time?
mm, no, currently we have one SKU for the BBU module, which can provide 5 minutes capacity. And it's fixed 3 kilowatts. But you can install less number of modules in the shelf. For example, you can install, instead of 6, you can choose to install 5 of them or 3 of them for less power or capacity.
I see. And if they want more, they can have two battery shelves in the rack.
Yes,
Does that work?
yeah, that will work. We can use the same idea as power shelf. We can add a share pin, so the 2 BBU shelves could share current and work in parallel. So that will provide more wattage and capacity.
I see.
Yeah.
So through this PMC or PMI RJ45, they can plug 2 units together to have the shared current, and they
Yes.
can have two BBU shelves to work together.
Yes.
All right. The other question from Samir is that what is 5 amp charging? What is that in C rate? Is it like C 10%
C
of C?
rate. Oh, C
Yeah.
rate. Okay. It's 1.6 amp hour battery cell. So we have 6P. So 5 amps is about 5 divided by 6. And then let me calculate.
Okay.
5 divided by 6. So each cell is 0.8 amps. So it's about 0.5 C.
So about 50% C, yes?
Yeah. About 0.5 C.
So 5 amp is like half a C.
Half
charge.
a C. Half a
Half a
C.
C, yeah.
Yes.
Okay. It's not that, it's good actually.
Mm.
Yeah. I don't see any other question, but I'm curious on this slide that you have. Why is the handle vertical? Why couldn't, is there any problem? Could you make it horizontal?
I think I don't know exactly the answer, but maybe Steve knows. I'm not sure Chen Yu is online. Yeah.
I don't think Chin Yu is here, but
Okay.
I think this was more ergonomics of having it kind of in the center of mass as opposed to having it offset from the bottom so you can get your fingers around a little bit easier.
I mean, during the plugging in and sliding in and out, having the handle vertically, will it cause any, will it be okay compared to the conventional way that I have in my mind that you have a handle horizontal?
No, I mean, I don't.
Yeah, because the latch, I think it has something to do with the latch position. The latch is also vertical to save the spacing. I think Cheng Yu has a reason for that. Because the latch is vertical, so the handle needs to be vertical. So you can use one hand to operate the insertion and removal.
I suspect if you look inside the BBU, right, you're gonna have more space vertically than you got horizontally, right? So you use that latch space on the top rather than on the side.
All right. One last question. What is the maximum long-term operating temperature for BBU? Can we use immersion cooling for BBU?
No immersion cooling. The maximum temperature is 45 degrees C, but for long term, it's 35 degrees C.
I see.
Yeah.
And then why do you say we cannot use immersion?
I guess immersion means you use liquid cooling.
Yeah.
We didn't consider liquid cooling for the BBU shelf design.
I see. Okay.
Yeah.
I mean, they probably need to do some revisions on the design to make it liquid cool compatible, but it's not currently designed for.
Right.
Yes, same as PowerShell and rest of the rack.
Mm. Yes.
All right.
Mm.
Thank you so much, David, for your time. That was a very great and informative presentation.
Mm.
And with that, we move to the next presentation.